Okay. Any questions on the last little bit of asynchronous stuff about diuretics, just the general physiology of them, and also that spironolactone, for example, the weird steroid thing? Is that all? I think the video is pretty clear. I did make an error when I talked about the loop diuretics and where they're acting, but I think it's very clear that they inhibit sodium and potassium reuptake or reabsorption, because the main ions that are being excreted are sodium and potassium, more sodium. And anyway, so yeah, I slipped up a bit, but I explained myself in the video. Any other thoughts on that stuff? Also, I think you guys all got the email that I did assign that first homework assignment. Hopefully you got that in time to do it. It's not that hard, but it's due on Friday at midnight, essentially. And I'll probably be doing that, making these things like I'll assign them on Friday and they give you a week. I think that's pretty reasonable. They're all about the same difficulty level, and I mean so I don't know. And if you have questions, you can always ask me too. All right. So we're cool. Everybody's cool.
I have a question about the homework assignment.
Yeah.
So I saw that you said like we should just cite our references if we use any like internet or whatever. Are we permitted, or like are you okay with us using like any resource off the internet if we like find something that explains the mechanism or like a similar mechanism as reference, or like?
See, that's a hard one. I mean, I think that's reasonable. And if it seems to me that you're pushing it a little bit, that I'll let you know. But I think that's just reasonable. I mean, these are kind of like open note courses or assignments. I don't want you an open resource assignments. I mean, obviously, if you're just directly copying the answer from somewhere, that's a little different. But using literature,
as long as we understand what we're actually doing.
Yeah. So there's a line between what's reasonable and what's not, and I mean, I think you guys probably know that line. I mean, so
yeah, for sure. And then are you still holding your office hours in person tomorrow, Thursday, 11 a.m.?
Yeah, every Tuesday, Wednesday, and Thursday. So
we're just free to stop by.
You're totally free to stop by. Yeah.
Cool.
Yeah, and usually about now, Organic 1 students start asking me stuff, but they haven't yet. So now, but obviously, I mean, you guys are allowed to be there too. And if there's 100 Chem 233 students, I'll probably give them a little priority, but it's unlikely that it's going to happen. So we do have our first Organic 1 exam next Thursday, so they might start coming pretty soon.
Cool. Thank you.
All right, cool. Any other thoughts or questions about the asynchronous stuff? Okay. You can always email me if you have just little questions and stuff. Okay. All right. Okay, so I'm going to try to do this again. Let's see. Okay, we are recording, I think. I set that up. Yeah, recording. All right. So, all right, so we're doing what we did before, kind of walking through your organic knowledge as you learned it, potentially with the Volhard-Shore book, but really any book, and kind of reviewing little bits of well, putting it into the context of pharmaceuticals, right? So we're on to number 4, which is kind of, again, walking sort of in sequence of the Volhard-Shore book. And I'm going to just call this reactions of alkenes and alkynes, which is kind of where we are in the book, which is sort of VS10 through VS13. And I'm actually gonna not really do much here. I'm gonna say not very important because we've seen alkenes and alkynes a little bit, but it's not like a worthy of a whole new topic. So not an important part of this review. But a couple places you've seen them. Well, alkenes you saw in tamoxifen, the synthesis of tamoxifen. Remember, it was some kind of like you know, you had a couple of aromatic rings, I think like a methyl group or ethyl group over here, and it was an interesting alkene, which is the breast cancer drug or the estrogen receptor antagonist. Alkynes, you know, alkynes are usually not really found in drugs. I have to really think hard about that. But alkynes are great synthetic intermediates. So of course the triple bonded things, right? So I think the most recent use of alkynes that we saw was a synthetic intermediate, and that was that spironolactone synthesis. That was the diuretic drug, potassium sparing diuretic drug. And it was interesting that we used alkyne just as a nucleophile. It's like we attached something using the alkyne and then we immediately reduced it. So it's not like we even kept it as an alkyne. We turned it into an alkane. And that's, you know, that's a common use of alkynes. It's just something you can attach to something and then kind of turn it into something else or whatever, right? Okay, so let's see. All right, so now we're on to number 5, which is sort of continuing the book, Aromatic Chemistry. VS 15 and 16. So this is these are the chapters on aromatic chemistry in Bullard Short. So let's just show a couple examples of drugs that are based on an aromatic ring that you can make really easily, and review a little bit of your chemistry of aromatic compounds. First one is ibuprofen, which is a very simple over-the-counter painkiller. It's the class of drugs are called NSAIDs. Non-steroidal anti-inflammatory drugs. I think I have yeah, I have a little overview of this I'll show. I think I'll probably show it here in a few minutes of kind of the general like the basic biology of NSAID drugs, and ibuprofen is a great example of this. So this is also called Advil. And okay, so the molecule is pretty simple, but it's a fun short synthesis that uses aromatic chemistry. So it's a benzene ring. It's got that little thing on it. It's got an alcohol, and a carboxylic acid. Does anybody know what IBU stands for in terms of the structure? IBU? Ibuprofen. Maybe you've never thought about that before, but looking at the molecule, does that stand out as anything? Somebody said it. Isobutyl. That's right. Isobutyl. And that's an isobutyl group, right? And I actually teaching Organic 1 right now. I just taught the students about isobutyl groups. So it matches my Organic 1 stuff. But yeah, that's oftentimes the name of a drug is kind of refers to something in the structure, which is kind of cool. Okay, so I'm just going to jump to the beginning. That's the final product. I'm going to sort of just jump to the beginning of the synthesis. And the main thing they're doing is just sort of attaching this piece. This piece gets kind of added. So they start with just isobutylbenzene. Isobutylbenzene. And then they do a reaction, that one of the key reactions you learn in organic too, which is FeCl3. Actually, it's aluminum. AlCl3, I'm sorry. I got that wrong. So it's these two things, and reacts with the benzene. And that attaches a ketone to the benzene. So what to say about this all? Anybody know the name of this reaction? I mean, it is one of the things you learned in organic too, but you may not remember the name. It's a way of attaching, whoops, sorry, one second. Yeah, it's a way of attaching a ketone, right? And it's like it's acid chloride and this aluminum trichloride. They come together and kind of like they talk to each other. It's like a Lewis base, Lewis acid thing. And essentially this just jumps off and then you get something that gets attacked by the benzene. This whole thing is called Friedel-Crafts. You may or not remember that. Friedel-Crafts acylation. Acylation refers to attachment of the ketone. So the ketone gets just attached right there, okay? In a nutshell, when this thing falls off, it makes something that looks like that. Is weird. It's the CH3 C triple bond O, and then the benzene just kind of attacks it. The benzene attacks it, and that's what the Friedel-Crafts acylation is. So that, like the benzene attacks it. I'll just draw what that makes. Something like that, and then it loses the proton. That proton gets taken off, and then it remakes the double bond. So that's what Friedel-Crafts acylation does. It's a little congested here, I'm sorry. Usually I give myself some more space. Anyway, so a base takes the proton, and then it remakes the double bond, and then you get this ketone, all right? So what do we have to do next? From the ketone to make this thing, how's that? What's gonna happen? To go from the ketone, this ketone to this carboxylic acid and the alcohol. So what they do, sorry, it's a little congested here. They do is they react this with sodium cyanide, because what they're going to do is attach that extra carbon. They have to attach an extra carbon, and cyanide is a great way to do that. Na plus Cn minus, and that carbon will basically become that carbon, right, in a little bit. So this is really cool. It just attacks, and now it attaches that extra carbon. So just circle it, attack. Cyanide is a great way to do that. This is actually another topic in the book. This is VS20. Well, Hershor 20. This is, and it makes something called, well, has a name. Anybody know the name? Is there an OH in ibuprofen somebody sent? And yeah, the answer is yes, there's an OH right there. I believe that structure's right. Let me I just want to double check. I'm pretty sure that's all right. One second. I'm gonna Google. My notes are usually right. Okay, actually, I think there's an extra step that I'm missing, and I'm going to research this. Yeah, and I can actually I believe that this OH gets lost in another step, so I'm going to fix this. But for now, we'll just keep going with this. All right, so give me a second here, and because that OH can be removed really easily, and I believe that is actually the case. Thanks for catching that. Anyway, okay, so first thing is going from the C triple bond ends to the carboxylic acid. That is an easy step. And I'll just mention that real quick. It's H3O plus acid. Acid simply converts the C triple bond N into the carboxylic acid. That's also a standard organic 2 reaction. It's a long mechanism too. I'm not going to show it, but essentially the nitrogen gets protonated. And then water just attacks the carbon and converts all the N bonds to oxygen bonds. So that's actually that is a pretty easy thing. That's also a VS20 reaction. Okay, so we get to this point. Let me just tell you how to take off the hydroxy, and that is actually required to make the final drug. Okay, so to do that, you have to take off the hydroxy group. This is actually an advanced reaction, but it's just a common reagent. We just need to make a carbocation, so have it fall off, and that's just like HCl or something like that. So that will cause it to fall off and make a carbocation, a plus charge, and then that can be reduced with something called ET3SIH. So this is essentially an H minus, and the H minus will reduce the carbon with a plus charge. So this thing falls off, you get a plus charge, and then this thing kind of turns it into hydrogen, and you see, there's a hydrogen right there. Okay, so anyway, yeah, for a second, I actually had the structure of ibuprofen wrong, but there is this extra step to remove the hydroxy group, and that's how they do it. Okay, so anyway, that was a little bit, I think usually my structures are correct, but I guess I got this one wrong. Okay, this is ibuprofen though. All right, we cool with that? All right, so how do these NSAID drugs work? I have a couple little slides on that, so let's show that. All right, but in general, synthesis is pretty straightforward. They just have to do this extra step to remove the hydroxy group in the end. Okay, so let me show my little scheme. One second. It's loading. One second. Is it showing my cyclooxygenase scheme? It says basic overview, cyclooxygenase. Okay, cool. All right. So this is on the iLearn site also. It just kind of, it overviews the basic idea of how these drugs work and some of the controversy around NSAID drugs. And the drug target is called cyclooxygenase, right? Okay, so how does this work? Basically, pain, like inflammatory pain that we might encounter, like having a headache or something like that, occurs from kind of the metabolism of something called arachidonic acid. I'll show the structure of that in a bit. And essentially what happens is there's an ester form of arachidonic acid that's found in cell membranes. And it is converted to arachidonic acid through an enzyme called phospholipase A. So that kind of hydrolyzes some of the ester structures. And this actually is so inflammatory events will kind of stimulate this process and create arachidonic acid. And steroids, so steroid anti-inflammatory drugs like cortisones and things like that will actually inhibit that formation of arachidonic acid. Arachidonic acid kind of results in other inflammatory cascades and things like that. Okay, so arachidonic acid can be converted into these prostaglandins, which are other kind of messenger molecules that can be metabolized by cyclooxygenase. Cyclooxygenase is an enzyme that you'll see what it does in a second. Anyway, so drugs like aspirin and ibuprofen and Tylenol and things like that will inhibit cyclooxygenase. And that's kind of a way to kind of prevent inflammatory response. Interestingly, this can all happen in either one pathway or another, depending on which cyclooxygenase enzyme is being used, and that can cause different effects, I guess. So cyclooxygenase 1 can lead to kind of gastrointestinal issues and maintenance, GI maintenance, right? And sometimes when you use drugs like ibuprofen, you kind of prevent the maintenance and you get GI effects and like stomach upsetness and things like that with cyclooxygenase 1. And with cyclooxygenase 2, it kind of leads directly to inflammation. Now, these drugs can inhibit both enzymes, right? You might think, though, what if we could create a selective COX-2 inhibitor that only deals with inflammation, right? And that seems like it might be a logical thing to do to avoid sort of GI problems and stomach upsetness. That seems like it could be a big moneymaker too, right? Like if you could make a selective drug that only deals with inflammation, then you could be a billionaire, right? But what we're going to see is that people have done this, and some of the drugs work, but they also have like cardiovascular problems and might give you a heart attack. So it's not necessarily perfect. Okay, so anyway, this said, the drugs that we have over the counter, like ibuprofen and aspirin, they do inhibit both pathways, but not in a way that the side effects aren't that severe, and that's why we can still use them as drugs. Okay, so what are these reactions? Arachidonic acid is this weird polyalkene with a carboxylic acid. So all the cyclooxygenase enzymes, basically what they do, cyclooxygenase, it creates an oxygen cycle, a cyclic oxygen peroxide type thing, and a hydroperoxide here. And then there's a reduction event where the hydroperoxide, OOH, gets converted to an alcohol, and it's a different prostaglandin, PGG2. And there's other prostaglandins and other kind of reactions going on, but that's basically what cyclooxygenase does. Okay, so some of the good and bad COX-2 inhibitors are one thing called Vioxx, or rofecoxib. I probably mispronounced it. It's a benzene connected to a furan. No, I'm sorry, a lactone, a gamma lactone with a sulfone, so this kind of thing. And then there's also another one that is actually currently being used as a selective COX-2 inhibitor called Celebrex. And this is used in like rheumatoid arthritis and kind of like painful diseases like that. They actually have a similar structure, as you can see. I mean, it's kind of like a central 5-member ring type thing connected to like a benzene and then some kind of thing up top. Both of them, one has this S double bond O thing. This one has an S double bond O NH2. Does anybody know the name of those functional groups? The top one is it's called a sulfone, and the bottom one is called a sulfonamide. I think I had my chat open. I can't find it now. One second, sorry. Top one's a sulfone and its bottom one's a sulfonamide. Okay. All right. So one of the nice things about cyclooxygenase is that it's one of the early enzymes that we've been able to do X-ray crystallography with and actually design the drug to fit into the pocket, kind of. And I think I have a picture of that. Yeah. This is just one of the generic X-ray crystal structures of a selective COX-2 inhibitor co-crystallized with the COX-2 protein. And so it's cool. This being able to do this. I mean, you can do, it's called structure-aided drug design, where we're using the structure of the protein as a template to design the molecule. And drug companies can do this really well nowadays. So they can make crystal structures very quickly, and then they can do synthesis very quickly. If you do all of that, you can actually create drugs pretty quickly. If you are, if you're able to do all of those things kind of rapidly and do biological assays quickly, it's just a very nice way of doing drug design. So this is called structure-aided drug design. Okay, this just shows the protein a little bit larger and kind of how small the drug is relative to the enzyme. All right, so just another example of this co-crystallization as a, what does that mean, co-crystallize? That means they grow the protein as a crystal structure, a crystal, and then they soak in the molecule and it finds its binding site. And then they analyze it with X-ray crystallography. So yeah, it's a great technique. And this is kind of like that HIV reverse transcriptase inhibitor that we were showing. In that case, it's the molecule is permanently attached into the growing DNA strand. So it's a little different. This is a reversibly binding inhibitor of an enzyme. All right. Cool. Any questions? Okay. All right. So let's go back to my thing. Okay. All right, so on away from ibuprofen as one of these examples. But let's continue the theme of aromatic chemistry. And that general reaction where we're attaching stuff to a benzene is called EAS. So that's the abbreviation I always use for it, which is electrophilic aromatic substitution. As a, the basic idea is you got a benzene and you're attacking an electrophile. Like that, right? That's essentially what we did to attach that ketone thing to make ibuprofen. Of course, this attacks, you get your electrophile attached, you got an H, you got a plus charge, and then some kind of base takes the proton and finishes it off. So, all right, so let's see another example. Totally different class of drugs. This one will be oxalinic acid. Oxalinic acid. This is one of these quinolone antibiotics. Quinolone antibiotics. What they do, and I'll show the structure in a second. I'll show the structure right now, and then we'll show the synthesis of it. So what's a quinolone? Well, this is what we call a quinoline, basically, quinolines. So these are found in like antimalarial drugs, right? Quinolines. But a quinolone has a ketone right there. So now it's a quinolone antibiotic drug. And it's got a carboxylic acid up top and an ethyl group. So it's a pretty simple molecule. These molecules, how do they act as antibiotics? Well, I mean, bacteria have their own set of drug targets. It's pretty logical. And so there's different ways to attack bacteria. And the way this drug works is it inhibits an enzyme called DNA gyrase. And DNA gyrase is probably involved in DNA in some way, right? And so what it does is so what the enzyme does is it reduces helical strain in bacterial DNA. And why would that be important? Well, DNA structure is kind of sensitive, and when these enzymes, basically what they do is they kind of nick the DNA and allow strain to be lost, and so it kind of opens up the DNA and allows the helices to reform. And if you kind of prevent that from happening, it kills the bacteria basically, which is pretty cool. So as a class of drugs, this is similar to well, there's a whole class of these quinolones. Ciprofloxacin, which is one of the kind of common fluxacin, which is one of the standard antibiotics you would receive if you have a bacterial infection. So it's the same kind of concept, and it's the same class of drugs. If you look up Cipro, it kind of looks like this. It's got the quinolone structure also. So basically what the drug does is the drug causes double-strand DNA breaks. In your bacteria. And essentially what that does is it kills the bacteria. So it prevents bacterial replication. And ultimately the bacteria dies. So that's how it's an antibiotic. All right, so let's talk about the synthesis of this thing. They essentially are able to build this whole, they take the left side and they attach the right side to it, which is pretty cool. It's a pretty simple thing. They also make this little connection from the nitrogen to the ethyl group. So they basically, yeah, they're going to essentially start from that and then add this other stuff through a couple steps. So let's show that now. Okay. All right, any questions? Chat. Okay, cool. All right, so we're on oxalinic acid. Draw it one more time. Okay, and so they start with this left part of the molecule. Looks like that. And they are going to nitrate it right there. So you can see that nitrogen will eventually become that nitrogen, right? Anybody know how you nitrate a benzene? Nitrate a benzene. One of your organic, probably organic 2 reactions. Something with nitrogen in it. It's something like that, right? It's HNO3, H2SO4. Okay. This aromatic nitration. That's a nitro group, right? Nitro group. Okay. And this is just reviewing your organic chemistry of aromatic rings a little bit. Does anybody, let's just go back briefly to the ibuprofen. Because the one thing I want to mention was when this happened and we attached the ketone, why did the ketone go on the opposite side of the isobutyl group? What's that called? It's like a something director. Do you remember this stuff?
Orthopara director?
It's an orthopara director. That's right. This thing is an orthopara director. Of course, ortho means next door, right? And then you got meta, right? And this is para, right? So this actually went to the para position, right? So it's an orthopara director. Ortho is usually disfavored, but para would be preferred because of the, it's kind of far away from this isobutyl group, right? Okay, so yes, it's an orthopara director, and that's why it goes here. Generally speaking, electron donating groups, an alkyl group with a CH2 and all the carbons, those are considered an electron donating group. EDG, electron donating group. electron donating group, and it's donating electrons into the benzene, and through a kind of organic 2 mechanism, it forces things to go to the para position. All right, we cool with that? So it's a ortho para director and an electron donating group. All right, back to here. What kind of group do these oxygens appear to be? And they're both, the same. Are they ortho para directors or not? Well, yeah, they are. And I mean, the thing is, though, that, this looks like it's being pushed para to this oxygen, right? So this oxygen is putting it there. Well, of course, I could say, well, this goes to put it there, and that's the same molecule. So, I mean, it's like, yeah, they're kind of, they're the same, right? And they are ortho para directors. Any oxygen with alone pairs of electrons are ortho para directors. So yes, ortho para director. Okay, cool. All right. Yeah. So, but when I say ortho, para, in this case, I'm just saying para to the top one, but you could totally say para to the bottom one. All right. So you got your nitrogen. That's cool. Now we're going to do another organic 2 reaction. Convert that nitrogen O2 to an H2, an amine. We're going from NO2 to NH2. Anybody remember how to do that? That's also an organic 2 reaction. Is it an oxidation? Is it a reduction? You have a bunch of bonds to oxygen. Now you have bonds to hydrogen. So probably not an oxidation, but it's the opposite of oxidation, reduction. Yeah. And anyway, so this is very easy. Reduce H2 palladium. This is a reduction of the nitro to a NH2. Okay. All right. So we did that. Now, maybe a more fun thing happens. I'm gonna give myself some space. Okay, so we have ethoxy, acetyl bond O, ethoxy, and we got an OET. All right, so this is going to be the building block that kind of installs all of this stuff. You can kind of see how it lines up, right? Like this stuff kind of lines up with that stuff. All right, so now we're ready to kind of attach these 2 pieces, and this is going to become that whole ring here in a second. So the way this happens is really easy. Essentially, I'm just going to have this guy kind of sneak around there, okay? And it's going to come attack here. That's kind of what we call a Michael reaction. It was another organic 2 reaction, Michael reaction, where a nucleophile attacks an electrophile through a double bond like this, okay? All right, so what's going to happen is this. Let me draw the product, then I'll explain the mechanism. The product's pretty simple. I'll return to my little circles for my benzenes. Okay, so we got our oxygen. Okay, see what happened essentially is the nitrogen kind of replaced off this ethoxy group, right? See that? Nitrogen kind of is now attached where the ethoxy was, right? You might just say, oh, it just attacks and kicks it off, right? It just attacks, kicks it off. That's not true though. The reason is because that's kind of what we consider an SN2 reaction, like the nitrogen would attack and kick it off. But this is, you can't do an SN2 with a double bond there. So rather what happens is this kind of goes, it attacks, it kicks up there and then onto the oxygen. See that? The nitrogen attacks, the double bond breaks, makes a new double bond, and then the electrons go all the way on the oxygen. You get O minus up top, right? O minus. And then it swings all the way back down and kicks off the ethoxy group. So it goes all the way up, then it goes all the way down, back all the way down, and then the ethoxy group gets kicked off. It's probably a two-step process, right? Nitrogen attacks, electrons go all the way up. Then, as a second step, electrons go all the way down and kick off the ethoxy. And what do you get? You get this thing, it's attached, right? It's attached now, right? We cool with that? Any questions? I mean, I could draw it out. It'll just be a two-step kind of process. Okay, all right. So now what do we got to do? Now we got to build the ring. That's really easy. I think we could just cook this a little bit. EAS happens. And you get the ketone. Actually, I'm sorry. Well, you get the alcohol there. It'll convert to the ketone in a second. Okay, so it's essentially the benzene attacks the ester and kicks this off. And that's essentially what we call EAS. Like we just talked about that, how a benzene will attack an electrophile. So here the benzene's attacking the ester. The ester is an electrophile, right? Maybe just to make this a little more clear, let's just draw the benzene out. Alkene, alkene, alkene. All right, so we have our, see that? I just draw the 3 double bonds of the benzene. Okay, and so all it does is a double bond attacks. Okay, this is another case where it doesn't just kick off the ethoxy. Electrons go up, electrons go down, and then it kicks it off. So I'll abbreviate that. Electrons go up, then the electrons go down, and then electrons kick off and make the ethoxy falls off, right? All right, cool. And then we have the ring. Then we have the ring. And then it just, you know, the double bonds reform and stuff, and you get this. All right, so cool, that's cool. We essentially started with a very simple molecule, attached nitrogen, reduced it, snapped on this nice building block, and it's cyclized through an EAS reaction. We're very close to the product now. I think all they do is NaOH, which, what does that do to the ester? NaOH does something to that ester. Anybody know? You can see what it turns it into. Goes from an ethyl ester to a carboxylic acid. So it hydrolyzes the ester into a carboxylic acid. So ester hydrolysis. I think that's VS like 23 or something like that. VS 23, ester hydrolysis. Okay. All right. Then they essentially just have to attach the ethyl group, right? So maybe what do they use? They use they have to attack ethyl with what kind of group on it? The nitrogen's going to attack something with a ethyl group on it. And I think they just use like ethyl iodide. So it's like a leaving group, right? So the nitrogen will directly attack this, kick this off, and then we got it. Then we got it. A little bit of electron movement to get to the final product. But that's it. That's how they do it. They start with a pretty easy molecule, build that extra ring, and then they just attach some stuff like the ethyl group and cleave off the ester. And there it is. Cool. Okay. All right. And now I got, oh yeah. I got one more and I'll probably stop for the synchronous lecture. Moving along, next set of reactions, getting close to the end of the Volhard-Shore book, and then we'll move a little more into pharmacology stuff. So now we're on to this, the chapters of like carbonyls, ketones, aldehydes, and stuff. And something called enols. Enol, what's an enol? It's related to a ketone or keto-tautomer, I guess. But so these are different ways of referring to the same molecule. They equilibrate. That's called an enol. And then there's also the reaction called an aldol reaction. We'll see that in a second. This is via 17 to 21. Cool. The aldol reaction is a very simple reaction. I'll just show an example. Acetone will react with itself. So essentially, a ketone can be a nucleophile. A ketone can also be an electrophile. So when a ketone reacts with itself, so molecule A reacts with another of itself, we'll say, yeah, then it makes this kind of product. That's called an aldol reaction. And also, there's the other class of stuff going on in this little block are carboxylic acid derivatives. Which are like amides, esters, etc. And that's all this group. Okay, so let's show a pretty cool example of another little synthesis that kind of uses some of the weird ketone chemistry and some of the like chapter 17 stuff. All right, so this one is going to be another one of those antifungal drugs that we talked about before. It's called ketonazole. Ketonazole. Remember, like micronazole, like because myconazole. It was one of the early ones we talked about. You'll recognize the general structure here in a second. So it's antifungal, and it was like myconazole and econazole. And those are the things that inhibited the fungal cell membrane synthesis. Fungal cell membrane. Whoops, fungal cell membrane synthesis. Okay, so and it has a really interesting structure and kind of a way to make it. So let's draw it at the bottom here. I'm going to draw a benzene sideways, chloro. And then we got this weird looking thing. Because you might remember that. You might remember that from Organic 2. you might remember this, right? That thing. Yeah. Does anybody remember that? I don't know. There's more to it, but let me start with that because it actually has another thing, which is over here, and it's like a benzene and a nitrogen and another nitrogen and a amide. Okay. So where did you see that though? Where did we see this? This is a early, organic or mid-organic 2 concept. A mid-organic 2 concept. Anybody remember that? Name of that maybe? Anybody know the name of that? Protector. Somebody said protector. Yeah, that's right. It's kind of a protecting group of a ketone. So like you could imagine a ketone there, right? And then you could turn the ketone into this thing. And the thing is called an acetal, right? And then you could do some other reaction on the molecule. So right? And this will protect the ketone while you work on maybe the chlorobenzene or something like that, right? So this is a protecting group. It's called an acetal protecting group. Okay, so just saying that again. Like if I have cyclohexanone up here and I want to convert it into the protected derivative, acetal. How do you do that? Anybody know? So you react it with something, right? You react that with something to make that. What's the something you add? Well, it's that. It's just the top part, which is ethylene glycol. And a little bit of acid. And so these things react. That reacts with these things and it makes that. And that's like a protected ketone. You have a ketone plus blah, 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 this thing. You make an acetal. That's a protected ketone. And then I could do other stuff in the molecule. Well, this kind of will look like that, which is sort of cool. All right, so let's show the synthesis now. Okay, so just like we did with miconazole and euconazole, it kind of starts from the same point, which is cool. So we're going to draw a little benzene here, chloro, all right, and then a ketone, a bromoketone. A bromoketone. All right, so that you can see how that's going to somehow map to that stuff. Okay, so just like you did here, we're going to make a acetal. There's our chloro. Let's draw it nicely. Chloro. But this is going to be a funny acetal. That looks like that, but with an extra hydroxy group. Isn't that weird? I mean, if you're used to this, maybe, or you remember it vaguely from organic 2, then this looks kind of cool, but a little weird, right? I agree. It looks a little weird. So what's the reagent we're going to use? Any guesses? How many carbons will the reagent have on it? How many carbons will it be? It's going to look like roughly this, right? How many carbons is that? Well, 1 carbon, 2 carbon, 3 carbon, right? It's going to be a similar idea to this dialcohol, which is called ethylene glycol, or it's car antifreeze. It's the stuff you add to your car radiator to prevent it from freezing, like in Lake Tahoe or something. Anyway, this is a trihydroxy group. I think it's it's in the fungal, or it's in the cell membrane, right? Is it glycerol? Let me double check that. I think it's glycerol. Glycerol. I think that's what it is. It's lipid or bilipid membranes and stuff like that. Glycerol. I think that's glycerol. Yeah, I think it's glycerol. Yep. Okay. So yeah, they add glycerol, which is three, it's hydroxy, 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 3 carbons, right? And then a little bit of acid, and it makes that weird acetal. All right, cool. So that was cool. And now it kind of, you know, now all we got to do is attach this weird thing, right? We also got to attach the imidazole. Remember the imidazole? We did that earlier as well when we did miconazole. This is miconazole, econazole. They both had the imidazole right there also. Okay, cool. So that's all we have to do next. It's really easy. So let's do those 2 things, and then this one will be done. Okay. I think what they do, the first thing they do is they actually protect the top alcohol with acid chloride and a base. So this is really easy. The oxygen attacks the carbon, kicks off the chlorine, right? Oxygen attacks, kicks off the chlorine, and the base just takes off the proton there, right? And that just makes an ester, linkage from oxygen to carbonyl. So that's actually really easy. Yeah. Oops, sorry. Space is tight. I'm gonna redraw it one more time. Sorry. Okay, let's try it one more time. A little more space. Draw my bromine going down. Okay. And then we have oxygen, benzene, and pH. See what I did? That's pretty easy. All we did was we attached that. We converted the alcohol plus acid chloride to an ester, okay? And this is actually a protecting group. This is a temporary, it's a PG protecting group, all right? We cool? What do we have to do next? Well, attach the imidazole. That's really easy. Remember how we do that? Super easily. If you look back when we did miconazole, econazole, it's just we throw in imidazole. We just throw in the reagent imidazole. It kicks off the leaving group. So that's really easy. So that is imidazole. It just swings in and attacks, kicks us off. Okay, that's easy. And then we have imidazole attached. Okay, there we go. At this point, I just stop because it's pretty straightforward and not that big of a deal. But essentially, all they got to do is deprotect this, remove the ester, and then kind of attach this stuff. And there's a couple steps. I forgot exactly how they built this. It's not that big of a deal. But anyway, I just wanted to kind of show, well, what did I show here that was kind of cool? I think the cool thing was that weird linkage using glycerol, which is, again, the most common use of glycerol is a component of our cell membranes, right? And they use glycerol as kind of a building block to make an acetal, and then they hang stuff off of it, which apparently affects the activity of the drug. And this thing, you know, changes the properties of the drug and the binding to the enzyme that, you know, the fungal cell membrane enzyme. Okay, all right. I think I'm probably gonna stop here. We have a couple more cool things to talk about. We're gonna slowly transition to more pharmacology, biology, but hopefully this is interesting to you, to see how these, well, you know, how the things are, these common drugs are synthesized, what the basic biology of them is, how they interact with their drug targets, a little, you know, in kind of cartoon terms. Okay. Any last questions before we stop today? And I'm gonna double check on the ibuprofen thing, because I think I did. I think I was right in the end, but I just want to double check that I got the end part correct from memory. All right. Okay, I think we're good. And let's yeah, I'll record the asynchronous component and put it on the website, like always on YouTube. All right. If you guys have any last minute questions about the homework, you can email me, or come to office hours probably tomorrow, maybe. All right.
Can I ask you a question just about the requirements of the homework?
Yeah.
For some of them, like when drawing the mechanism, do you, because you use the words, I think just draw like simple strategies like that we use in our course, and just draw like the simple mechanistic arrows. Does that mean you only want us to draw like the mechanism out to the extent that it was covered in lecture, or do you still want us to use like supplementary material to figure out like the exact electron pushing mechanism for the reagents, even if you didn't draw out it fully?
Probably you can just do what we did in lecture. I think that should be fine. And for this, as we go a little further, I may ask for a little bit more, I guess. Yeah, doing a detailed literature search, I don't think that's really necessary right now. I'm just trying to make sure you guys are following along with the lecture. And I'm going to ramp up here and there on some topics and mechanisms, but I don't obviously show every little thing.
And then also for like our references in our homework is just including like a link fine, like if it was like a picture we found like drawn out of like a mechanism.
Yeah,
like...
that's fine. That's okay. A web link that I can double check. Yeah.
Thank you.
Cool. Any other questions? All right. Have a wonderful rest of your Wednesday.
I have a quick question regarding office hours tomorrow.
Yeah.
How long would you be on campus tomorrow?
So, well, I'm around almost every day, all day. My office hours are technically 11 to 12. That'd be the most ideal time to meet me. If you need to meet me at a different time, that's possible. Just email me, and I can try to make it work. I do teach organic one also a little later, so 5 o'clock. But I'm also doing other stuff. So.
Okay, all right, that's okay.
Yeah, if you can do 11 to 12 would be wonderful if you could make it work. Okay,
perfect. Do you also have office hours on Friday or just Monday to Thursday?
No, it's Tuesday, Wednesday, Thursday.
Okay.
Tuesday is 10. Wednesday is 10:30, and no, it's Tuesday. Sorry, Tuesday is 10. Wednesday is 10:30, and Thursday is 11, and they're an hour each. 10,
all right.
10:30, 11.
All right, perfect. Thank you.
Cool. All right. Cool. All right. See ya.